In this video, I'm going to talk about the graph of a polynomial. In particular, we're going to talk about a polynomial's roots and the multiplicity of those roots. Let's start by considering factors of this polynomial p of x, which is x minus 1, then times x minus 2, and that whole factor raised to some power, which we will vary through examples, and then times x minus 3. So first of all, let's consider that this polynomial has a factor x minus 2 to the first power. So inside that box is just a first power there. Okay, so what is the multiplicity of that factor? Well, the multiplicity of that factor is just the exponent that it's raised to. So just 1. 1 is the multiplicity here. Okay, so this factor with a multiplicity of 1 corresponds to a root of x equals 2. X equals 2 causes this factor to go to 0, so it causes the whole polynomial to go to 0, so it's a root of the polynomial. So what does the polynomial look like around that root? What does it look like near x equals 2? Well, there's two possibilities. So the first possibility is that it's coming from the negative side here, and then it goes straight through the root 2 and then ends up on the positive side, like that. Okay, so that's one possibility. The other possibility is just the opposite scenario. Still a straight line, still going through 2, but this time it's starting from the positive side. So starting from the positive side and then coming down to hit the root and then going through to the negative side. Now, to make things concrete, let's give an actual example of a function, a polynomial having a root of x minus 2 to the first power. How about just y equals x minus 2. That's the simplest example we can do. It's just that factor, and let's go ahead and draw the graph of that. So that has a y-intercept of negative 2, and then slope of 1. So up 1, over 1, up 1, over 1. So it's really going like this, just a straight line through that root of 2. Okay, so let's move on to the other factors. Before we do that, let's go ahead and recap this factor though. So this is the simplest case, x minus 2 raised to the first power, and we call this a simple root. It has multiplicity 1, and it just looks like a line. It's roughly like a line around that root. It just goes straight through the root, and it can go from negative to positive or positive to negative. Either way, it's just going to be a line straight through that root. An example of that is y equals x minus 2, just a line straight through that root of 2. Now let's move on to a more complicated case, the factor x minus 2 squared. So this time multiplicity is not 1, but 2 this time. It's just the exponent up there. And what ends up happening for p of x near x equals 2 is instead of going through the root like it did for simple roots of multiplicity 1, it's going to just barely touch the root and then come back. So it might be coming from the positive side. So go like this and touch the root and then double back on itself like that. Or it might be coming from the negative side and then touch the root and then double back on itself like that. A concrete example of this would be, how about the function y equals x minus 2 squared? So that's just like a parabola going like this, just shifted over 2 units to the right. So it's going to look like this, and as you can see, it's once it hits that root of x equals 2, it doubles back on itself and it's going up in both directions. Now, one thing to note here is that this kind of scenario is really, it's the same idea for multiplicities of not only 2 but also 4, 6, 8, and so on for any even multiplicity. So same idea for multiplicity equals 2, 4, 6, and so on, just any even multiplicity. And the reason that is because you can think of y equals x minus 2 raised to an even power. That's always going to have a kind of parabolic shape to it. It might be a little bit flatter of a parabola near the root, but it's still the same idea that it's coming down and then hitting the root and then going back up, just doubling back on itself. Or it's coming up and then hitting the root and coming back down, again doubling back on itself. So either way, for any even root, you're going to get that doubling back on itself behavior, just touching the root and then coming back from where it came. Alright, lastly, let's consider the case of the factor x minus 2 to the third power in that polynomial. So to get the multiplicity, again, you just look at the exponent, that's 3, so multiplicity 3, and now this is going to be kind of similar to the multiplicity of 1, the simple root case, in that it's going to go just right through the root, but as it does that, it's going to flatten a bit at the root. So we might be coming from the negative side, and then as we approach through, it'll get a little bit flatter, and then it'll just keep going on like that. So it's kind of like that first case here, but it's flattening off a bit at the root. Likewise, we can be coming from the top here, coming from the positive side of y, and then flatten off a bit as we reach that root, and then continue downwards. So a concrete example of this might be the function y equals x minus 2 to the third, and that's just like a cubic function, just shifted to the right 2 units. So it looks something like this. And now you can see where that behavior of flattening off a little bit around the root comes from. But again, it's going through the root. It's not doubling back on itself. It's just going through the root. Now this is the same idea for multiplicities of not only 3, but also 5, 7, 9, and so on, just any odd multiplicity. So let's write that down. Same idea for multiplicity equal to not only 3, but also 5, 7, 9, and so on. So any odd multiplicity, yeah. The reason that is because if you have x minus 2 raised to some odd power, it's always going to have this general shape, kind of like a cubic. As the power increases, it'll just get even more flat at the root itself, but it'll still have that same idea of coming to the root, approaching the root, getting flatter, and then going through the root, and then going back to its original upward climb here after being flat. Here's an example. Which of the following is a possible equation of the polynomial whose graph is shown below? So we've got a graph of y equals p of x, and p of x is one of these polynomials here. But which one is it? Well, why don't we take a look at the graph and use the behavior around the roots of the graph to figure out which one it is. So first of all, let's make sure that each root here is included in the polynomial. If there are any roots here which aren't included in these polynomials, then we can eliminate it. So let's go ahead and look at root at -1. That corresponds to a factor of x minus -1, or just x plus 1, and that's raised to some power. It's multiplicity, but let's not worry about that just yet. Let's make sure each of these polynomials has that, x plus 1, x plus 1, x plus 1, x plus 1. Okay, how about this one? Root at 1, so that corresponds to a factor x minus 1 raised to some power. Again, everything has that root, so x minus 1s and everything. Okay, and then 2, root at 2, so that corresponds to a factor x minus 2 to some power. And again, they all have a factor x minus 2. Okay, so we're not able to eliminate anything just yet because they all have the right roots, but let's take a look at the multiplicities. These all have different multiplicities, so we should be able to differentiate between some options here. Okay, looking at the first root, x plus 1. This is it's roughly a straight line going through the root -1. So that means that it's a simple root. Its multiplicity should just be 1. So multiplicity equals 1 for this one. And let's go ahead and make sure that we eliminate the choices which don't have multiplicity 1. So looking at the exponent on that x plus 1 factor, choice A has a 2 there, but that's not multiplicity 1, that's multiplicity 2. So it's not choice A. Choice B has x plus 1. It's really just to the first power, so yeah, multiplicity 1. So that's okay. But we don't know for sure that it's B yet. We have to check some other things. C, that has the exponent on x plus 1 is 3, which is not 1. So nope, not multiplicity 1 on that x plus 1 factor. And then D, the exponent on the x plus 1 factor is just 1. So yeah, multiplicity 1. So that's a possibility. Okay, so we've narrowed it down to B and D, and why don't we go ahead and look at the next root here, x minus 1 to some power. And this root, around the root, it's got a curvy behavior. It's curving and then doubling back on itself. So it's just touching the root and going back. And that just corresponds to an even multiplicity here. So multiplicity equals even. So we need an even exponent on that x minus 1 here. So looking at our two choices, choice B has x minus 1 to the third, but 3 is not an even exponent, so it can't be choice B. So choice D, it's got to be choice D, right? But let's just double check the rest of the roots to find out. So x minus 1 to the second power, that is indeed an even multiplicity. So that's looking good so far. Let's just check the last root, x minus 2. So that's going through the root, crossing from the positive to the negative side, but it's also flattening out a little bit at the root, so that corresponds to an odd multiplicity. So multiplicity equals odd for this factor. So we want an odd exponent on the x minus 2. And indeed, on this factor x minus 2, we've got an odd exponent, exponent of 3, that's odd, so great, perfect, so it's got to be D. So D is the polynomial whose graph is shown there. Here's our last example. We want to sketch the graph of this polynomial function y equals x plus 2 to the third times x plus 1 squared times x minus 2. So this time we have to actually take this function and construct a rough sketch of the graph. So how do we do this? Well, why don't we start by looking at the roots of this polynomial. So the roots correspond to the zeros of each factor. So x plus 2, that corresponds to a root of negative 2. X plus 1, that corresponds to a root of negative 1. And x minus 2, that corresponds to a root of 2. So let's go ahead and plot those. Roots are just going to be on the x-axis because the y value is 0 at the roots. So negative 2 is a root, negative 1 is a root, and 2 is a root. Okay, so how are we going to make the function go through these roots? Does it go like this, or does it go like this, or like this, or how does it grow? How does it go? So why don't we look at the end behavior first? So if we were to multiply all of this out, we'd get a leading term of, well, there'd be an x to the third times x squared, and then times x, which would make an x to the sixth power. And let's think about the end behavior corresponding to that leading term. So x to the sixth, that's, well, when we plug in positive numbers, that's positive number to the sixth, that's still a positive number, so it's going up like this. And how about when we plug in negative numbers? Well, negative number raised to an even power is still a positive number, so end behavior as x goes to negative infinity, y is still going to positive infinity. So it's going to look something like this. Okay, and now let's go ahead and think about, let's go from left to right, looking at this root of negative 2 first. So the function is coming down to this root of negative 2, but what does it do at that root? Does it just go straight through? Does it double back on itself? Does it flatten out a bit? Well, let's look at the multiplicity here. Multiplicity is 3. So that means it does go through the root, it crosses over to the other side, but it does flatten out a little bit at the root. So let's go ahead and make it flatten out a bit. So flatten out, kind of like that, and going through the root. Okay, and now the next root is negative 1, and what does it do at that root? Well, obviously it has to turn around to start going towards the root, but what happens at that root? Does it go through, double back, flatten out? Look at the multiplicity. Multiplicity is 2 here, that's even multiplicity. That means it's just going to double back, it's just going to touch the root and go back in the same y direction. So we're just coming to the root, touching the root, and then going back in the same y direction, going back down. Okay, great. So we've got these two roots, we've got the graph going through these two roots, and now let's just take care of the last one. So we'll make the function kind of go here, and eventually it has to come back to approach this root. And what does it do at this root? So look at the multiplicity. This is multiplicity of 1, really. That's just a simple root, so it just goes straight through the root, just kind of like a line. So we'll make it just go straight through the root like that. And here we go. There's a good sketch of the graph of this function. Now, just to be complete, why don't we go ahead and label that y-intercept as well, just to get in a scale of this, what this y-axis should be like. So we'll plug in 0 into the function. Y of 0 is equal to just 2 to the third times 1 squared times negative 2 to the first. Just plug in 0 for all those x's. And then, so that's 8 times 1 times negative 2. So just negative 16. So that's our y-intercept here. The y-coordinate is negative 16. So up until now, we've been considering polynomial equalities, where y is equal to some polynomial, or some polynomial is equal to some value. But in the future, we'll also consider polynomial inequalities, where, say, a polynomial might be less than some value or greater than some value.